Hi everyone! Today we're in lesson 5.6, which is solving exponential and logarithmic equations. In this lesson, essentially, we are just going to go through a lot of examples. Some of the examples we will solve a couple different ways so that you can see that you have various options. And we're going to go ahead and get started. So example 1, we have 7 raised to the 2x equals 7 raised to the 48. So here we have an exponential equation. And this one's not going to be too bad because I notice that each side has the same base. And if 7 raised to the 2x is equal to 7 raised to the 48, well then that means those exponents have to be the same. And 2x has to be equal to 48. So all I'm going to have to do is divide by 2 and see that x is equal to 24. Another way to take a look at this problem is if you have 7 raised to the 2x equals 7 raised to the 48. I don't know why I left so much space there. You could say, well, what I need to do is I need to be able to pull that x right here out of an exponent. So in order to do that, I need to take a logarithm. I'm going to choose to take a log base 7 of both sides and use my property. My property that says log base b of b raised to the x is equal to x. When I do that, I can use my property to see that log base 7 of 7 raised to the 2x just simplifies to be 2x. And log base 7 of 7 raised to the 48 just simplifies to be 48. And there I can see I divide by 2 and get the same answer as I did before, that x is equal to 24. But the property is really unnecessary if we're just using logic, that if I have the same base, then those exponents have to be equal. Let's take a look at the next example. Example 2. I've got log base 2 of x plus 6 equals log base 2 of 10x. So here again, I see I have log base 2 of this expression, x plus 6, equals log base 2 of 10x. And so using logic, I know that x plus 6 must be equal to 10x. And now I'm just solving this linear equation. I'm going to subtract x from both sides, giving me 6 equals 9x. And then I'm going to divide by 9 on both sides. Sorry, I'm running out of space here. So x is equal to 6 over 9, or 2/3. Now, you could have used a property to solve this problem too. Remember, you have a property that says b raised to the log base b of x is equal to x. Well, what you could have done, I'm actually going to erase what I have written here in the red, so if you need that, go ahead and pause. To show you what you could have done here, I said, well, I need to get this x plus 6 out of this logarithm on the left-hand side. So I'm going to raise the whole left side using the base of 2. And I'm choosing 2 so that I can use my property since the base of the logarithm is 2. And if I do that on the left-hand side, I also have to do it on the right-hand side to keep my equation balanced. So now I have 2 raised to the log base 2 of x plus 6. And that just simplifies to be x plus 6. And then I have 2 raised to the log base 2 of 10x, which just simplifies to be a 10x. And so you see I end up with the same thing I had before, and I've already solved this linear equation, and I know that x is equal to 2/3. So in these first 2 examples, these are really basic exponential and logarithmic equations where you have the same bases on each side. Now what we're going to do is we're going to get a little more complicated. Let's look here. I've got 2 times log of x minus log of 3 is equal to 2. And I've got to solve for x. The whole goal is to get this x by itself. So first what I got to do is I've got to condense this left-hand side into one single logarithm. So using my rules, I'm going to pull this 2 up. So I'll have log of x squared minus log of 3 equals a 2. And notice the base of this logarithm is a 10 because it's a common log, it's unwritten. Now I'm going to condense these 2 logarithms, and since I'm subtracting them, this becomes log base 10 of x squared divided by 3 equals a 2. And now at this point, you can either use the property, again, the property being that b raised to the log base b of x is equal to x. I can raise everything using a 2, or you can just simply use the definition of the rewrite. Remember that this definition of a logarithm is what generated this property that I just boxed in the first place. So remember the definition of a logarithm, that log base b of y is equal to x if and only if b raised to the x is equal to y. And so this if and only if means I get to go in either direction. So what I think I'll do is I think I will rewrite this logarithm as an exponential statement. So the base of this log is 10, therefore that will be the base of my exponential statement. So I've got 10 raised to the second power equals x squared over 3. And now I have a simple quadratic equation that I can solve after rewriting in an exponential statement, because the x squared that I wanted to get alone is now isolated. So let's simplify first. I've got 10 squared, which is 100. I'm going to start working right here. So I've got 100 equals x squared over 3. Then I'm going to multiply by 3 on both sides, giving me 300 equals x squared. And now I get to take a square root. So x is equal to plus or minus, I'm going to be able to pull a 10 out and have 10 square root of 3. We might as well go through that. So if I have the square root of 300, that's the same thing as the square root of 100 times the square root of 3, and the square root of 100 is 10. So that's where I'm getting that 10 root 3. Now the last thing I need to do is I need to check and see if either of these solutions are extraneous. Remember that I have the log base anything of a negative number. This does not exist. And we talked about that when we explored the graphs of exponential and logarithmic equations. So therefore, if I were to try and sub in the negative 10 root 3 here for this x, I would end up with a logarithmic expression that doesn't exist. So therefore, the negative piece is going to be extraneous, and the only real solution is going to be 10 times the square root of 3, based on the original statement that's given. If they had originally given me the next part where they told me this right here, this log base 10 of x squared, then it would have been fine. But that was not the original equation that was given, so therefore I can't use that negative. All right, let me draw a little barrier here so that I can make sure I separate example 3 and example 4. So in example 4, I've got 6 minus log base 10 again of 3x equals negative 2. So what's nice here is that I only have one logarithm I need to get by itself. So let's go ahead and subtract this 6 over. So I've got negative log of 3x equals a negative 8. Let's go ahead and get rid of that negative. So I'll have log of 3x equals a positive 8. And now the only way to get this x out of this logarithm is either to use the property or rewrite as an exponential statement. And I think I will rewrite as an exponential statement. So if I rewrite this statement, I've got 10 raised to the 8th equals 3x. And now all I got to do is divide by 3. Now that 10 to the 8th, I'm just going to leave it 10 to the 8th because it's a rather large number. And I know it's not going to be divisible by 3. So I've got x equals 10 to the 8th over 3. So what we saw here in example 3 and 4, where we saw logarithmic equations, where you either had to condense the logarithm down to 1, or you just had to get the logarithm by itself isolated before you either use the property or the definition of the logarithm. Again, both of them are right here and here. To get my variable out of the logarithm and isolate it. So let's look at some exponential equations, switching it up. So on the next example 5, I've got 8 raised to the x equals 44. So this is an exponential statement. I think the easiest way to get this x out of the exponent is to rewrite this as a logarithm using my rule. I'll write it over here to reference again. Log base b of y equals x if and only if b raised to the x equals y. So if I'm rewriting this, I'll have log base 8 of 44 equals x. And voila, x is isolated. Now, when I was in high school, my teachers did not teach it to me this way at all. What they said was what you need to just take a logarithm. Anytime you see this x right here in an exponent, take a logarithm. And they were very specific. They said take a natural logarithm. And I trusted them, so I did. So if I take the natural log of the left-hand side, I have natural log of 8 raised to the x equals the natural log of 44. Good deal. Now I can take this x and I can move it out front. So I have x times the natural log of 8 equals the natural log of 44. And now this is simple. To get x by itself, I just divide by natural log of 8. If I was allowed to have a calculator, well then I'd plug this in and get a decimal. Otherwise, I'd leave it natural log of 44 divided by natural log of 8. And now I want to point out, how on earth can these two things be the same? Well, it's because of my change of base formula. Let's review that really quickly. The change of base formula says that log base a of c is equal to log base b of c over log base b of a. And you can let the base be anything you want. So if you're going to let the b be e, you'd end up with natural log of c over natural log of a. And so let's take a look at what I got here in the red. I have log base 8 of 44. Well, the change of base formula says that this is equal to log of 44, I'm using a base 10 here, over log of 8, or heck, I could use the natural log of 44 over natural log of 8, which is what I had with my teacher's method that they always preferred. I really just prefer to use the definition of a logarithm these days, but whatever floats your boat, these are all correct. Let's look at example 6. So here I have another exponential equation. I've got this 6 raised to the x. I need to get isolated first before I can figure out what x is. So let's subtract the 2 from both sides. I've got negative 6 raised to the x equals negative 11. Go ahead and divide by the negative and I'll get positives on both sides. And there you can see you've got 6 raised to the x equals 11. And the only way to get that x out of an exponent is to take a logarithm or do a rewrite. So I think I'm just going to rewrite. When I rewrite using my definition, I have log base 6 of 11 equals x. And then you're done. If you want to rewrite this with a natural log, you can rewrite natural log of 11 over natural log of 6. You can write it with a common log if you're wanting to plug this in your calculator and you've got an older one like I do, and it doesn't allow you to do different bases other than ln or e or 10. You've got options. All right, let's look at example 7. It looks like it's going to be jazzy. So I have log base 3 of 7x plus 1 minus log base 3 of x minus 2 equals a 2. So here I've got 2 logarithms on the left-hand side. I'm going to need to condense these down to 1. Since I'm subtracting, I know when I condense down to 1 log, I'm going to have to take 7x plus 1 divided by x minus 2. And now I have log base 3 of 7x plus 1 over x minus 2 equals a 2. Now, at this stage, to get rid of this logarithm, I'm going to have to rewrite this as an exponential statement. So in my rewrite, I have 3 raised to the second power equals 7x plus 1 over x minus 2. And now I'm going to go ahead and clean this up. This is just a linear equation. I've got 9 equals 7x plus 1 over x minus 2. I need to multiply by x minus 2 on both sides. So on the right-hand side, I'm only left with 7x plus 1. On the left-hand side, I need to distribute my 9. So I end up with 9x minus an 18. So now I think I'll move this 7x to the other side to avoid having a negative. So I'll have 2x minus 18 equals a 1. Next, let's add this 18 over. So I've got 2x equals a 19. And then my last step, I need to divide by 2. So I end up with x equals 19 over 2. And there I am. I need to do one double check and just make sure when I plug in 19 over 2 that I don't get any negative numbers. So when I plug in 19 halves to my first one, I have 7 times 19 halves, which is a positive number, plus 1. That'll be positive. And then if I plug in 19 halves to the x minus 2 expression, I have 19 halves minus 2. And since 19 halves is greater than 2, I know that I'm not going to get a negative number there either. So I'm going to be all set. Now, the other thing I want to show you here is an alternate solution where you can use your property if you'd like. Since you have log base 3 of an expression equals 2 and you really want to get rid of the logarithm so that I can solve for x, what I could do is just raise both sides using the 3. So what would happen here is the left-hand side would become 7x plus 1 over x plus minus 2. And the right-hand side is 3 squared, which is 9. So notice that here, when I use the rewrite method, just rewriting the logarithmic statement as an exponential, and here, where I was looking at it from a property standpoint, you have the same equation, and therefore this will produce the same solution that I had here. So you can see that we're kind of increasing in difficulty and in complexity as we go through the lesson. And I am ready to move to the next problem, example 8. Okay, so in example 8, we've got 4 raised to the x equals 1/2 raised to the x minus 3. So here I'm thinking, man, it sure would be nice if those were the same base. Then that would be just like example 1, where I could just set the exponents equal to one another. Well, it's funny we should say that. Is there any way that I could rewrite this 4 and this 1/2 so that they have the same base? Well, I know that 2 squared is equal to 4. And I know that 2 raised to the negative 1 is equal to 1/2. So why don't I replace this 4 with the 2 squared? And let's replace the 1/2 x with 2 raised to the negative 1 raised to the x minus 3. I think I said that wrong. We're replacing, now I went to the wrong slide. We're replacing the 1/2 with the 2 raised to the negative 1. So all I did here was replace the 4 and the 1/2 with 2 squared and 2 to the negative 1. Now using properties of exponents, I know when I have a power to a power, I'm going to multiply these. So I end up with 2 raised to the 2x equals 2 raised to the negative x plus a 3. And now this turns into a problem just like example 1, where if you have 2 raised to the 2x, and that is equal to 2 raised to the negative x plus 3, well, that means that 2x has to be equal to negative x plus 3. And now all I have to do is solve for x. It's a simple linear equation. We'll add x to both sides, giving me 3x equals 3. Divide by the 3, and you get x is equal to 1. All done. All right, let's look at example 9. I've got log of 2x equals 2 minus log of x minus 5. So anytime you have logarithms on both sides of the equation, I'm going to have to condense down to one logarithm. And I can only do that if all the logarithms are on one side. So I'm going to need to add this log of x minus 5 to the left-hand side. So I'll have log of 2x plus log of x minus 5 equals a 2. Now I can condense, And since I'm adding these logarithms, that means I will be multiplying 2x times x minus 5. And that's going to require a distributive property. So I'll end up with 2x squared minus a 10x equals a 2. And now that I've got the log by itself, it's time for the rewrite or the property. Since I've used the rewrite the last couple of times, I'll use the property this time for those who prefer that. So here I have log, it's a base 10 here. So to undo this log base 10, I need to raise everything to the 10. And then what that does is the left-hand side, using the property, becomes 2x squared minus 10x. And the right-hand side becomes 100. All right, so now I have a quadratic equation, and I can't solve. I have a quadratic term here, and I have a linear term, so it's not going to be as easy as that last quadratic that only had the quadratic term. So I need to get one side equal to 0. I think I'll subtract the 100 from both sides first. So I've got 2x squared minus 10x minus 100 equals 0. I think since I'm looking at these coefficients, they're all divisible by 2. Let's go ahead and divide everything by 2 and get some more friendly numbers. So we've got x squared minus 5x minus 50 equals 0. And this is really nice because it gives me a front coefficient of 1, and then I'm hoping this is going to factor. So I know x times x will give me the x squared. So I'm looking for factors in the back that'll multiply to be a negative 50 and add to be a negative 5 when I FOIL this out. So it looks like negative 10 and positive 5 are going to do the trick. And now I can use my zero product property. Set x minus 10 equal to 0, giving me x equals 10. Set x plus 5 equal to 0, giving me x equals negative 5 as my two solutions. Now the last thing I need to do is I need to check the original equation and make sure when I plug in these numbers, I don't get a negative inside my logarithm. And 10 is going to be all good, but when I plug in negative 5 here, I get log base 10 of a negative 10. So therefore, this solution is going to be extraneous. All right, we're almost done. Got the 1/2. I've got 2 more examples. So I haven't used any natural logs or e's really, so I wanted to make sure we got a few of those in. So this next one, example 10, I've got e raised to the x plus 7 equals a 10. The thing about this is just to remember that it's still an exponential statement. So you can take your exponential statement and rewrite it as a logarithm. If I rewrite this as a log, I end up with log base e of 10 equals x plus 7. Then you can see that x plus 7 is no longer in the exponent. Now no one writes log base e. Log base e is natural log. So I have natural log of 10 equals x plus 7. And now to get the x by itself, all I got to do is subtract the 7. So you have x equals ln of 10 minus a 7. And that's it. Now, if you really want to use the properties, you can certainly use the properties. Remember, if I have natural log of e raised to the x, well, that's just equal to x, and that's coming from the same log base b of b raised to the x equals x property. So what you could have done here is you could have taken the natural log of both sides of the equation. I need to move this over a smidge. Okay. I could have taken the natural log of both sides if I had wanted to. Then the left-hand side would have simplified to be x plus 7. The right-hand side would have simplified to be natural log of 10. Notice that's the same equation that I have right here. So I would have gotten the same solution if I had used the property. All right, let's take a look at this next one, the last one. I've got 2 times natural log of x plus 6 equals a negative 18. So I got to get the logarithm by itself first. So I'm going to divide by 2. I'll have natural log of x plus 6 equals a negative 9. And now that I have the natural log by itself, I can rewrite this as an exponential statement. And if it helps you to rewrite natural log as log base e, go ahead and do that. So I've got e raised to the negative 9 equals x plus 6 when I do my rewrite. And now the only thing I need to do is subtract 6 to get the x by itself. So I have e to the negative 9 minus a 6. E to the negative 9 is the same thing as 1 over e to the 9th. So you might want to get rid of the negative exponent depending on how you're feeling. Another thing that you could have done if you wanted to use the property, let me get rid of this. Oh, I changed colors. It's not going to let me do it maybe. I don't know. Nope, it's not going to let me erase. No big deal. I'll rewrite it. So here, when you got the natural log of x plus 6 equals negative 9, if you want to use the property, remember you've got e raised to the natural log of x equals an x. So I could have just raised everything using an e if I wanted to. That would have given me an x plus 6 on the left-hand side equals an e to the negative 9. Now, notice that's the same equation as that I had here. So therefore, this will have the same solution. All right, guys, you have a lot of examples to work with here. So you are all set to do problem set 5.6 on your own.